All right. So I also have done some work looking at seeing what you can do to explain this excess of short timescale events by looking at bound planets. And if I have time, I didn't include that as part of my main presentation, but if I have time, I'll kind of go back and discuss it. But what I want to focus on is sort of what we've learned about the distribution of planets from various surveys, including microlensing, and where we can go in the future to better understand planet demographics and ultimately understand models of planet formation and migration and evolution. So just to get started, this is the standard mass separation plot, and looking at this plot, first thing you notice is that there's a ton of planets. And it's quite tempting to kind of look at this plot and notice that our solar system planets are sort of right on the edge of sort of this envelope of detections. Now we all know that there's detection efficiency issues that sort of that make that possible, but there's a lot of other caveats that are sort of hidden in this plot as well. And I kind of just want to go through them first, and perhaps most notably is the fact that each of these, all of these planets were discovered by different techniques, and different techniques are sensitive to different properties of the planetary systems that they discover. And in fact, none of these detection techniques are directly sensitive to either the planet mass, the true planet mass, or the semi-major axis. Yet we all plot them in this plane. And the reason that we do that is because these are the fundamental parameters that we want to know about these planets and about this population. And so looking further into this, if we plot rough sort of median detection sensitivity regions for these different techniques, you can kind of see why we have this envelope here. And again, these are sort of just median detection sensitivity limits, which is why you have some of the Kepler planets that dip below this curve. This is sort of a 50% level detection efficiency. And so what this does is that makes it very difficult to infer things about the parent population of planets that our observed distribution is drawn from. No single technique, and in fact no union of these techniques, is uniformly sensitive to this entire region of parameter space. But if you want to sort of get at what this true distribution of planets is and what this true population looks like, we must necessarily combine results from these different techniques. And so with the exception of high contrast imaging techniques, these methods of exoplanet detection are indirect. We rely on measuring things about the star, about the host star, or in the case of microlensing, a completely unrelated star, to infer the presence of a planet. And so what this means is this has direct consequences on what we actually measure and what we can infer about those planets. So in the case of radial velocities, we measure a period, which by folding in knowledge of the mass of the host star, we can get an estimate of the semi-major axis of the planet. And we measure a velocity semi-amplitude, which gives us information about the mass, but up to a degeneracy in the inclination. In microlensing, we routinely measure the projected separation in units of the Einstein radius and a mass ratio. And so in order to get a projected separation in physical units, we must know the Einstein radius of the object, and in order to get a true planet mass, we have to know the mass of the star. And these are not routine observables. We have to measure higher order effects. So just going back to this picture that we've probably seen many times throughout this conference, in a microlensing event, we have this chance alignment of two stars, and light that would normally not reach the observer, in this case us, is instead deflected by the intervening lens mass, and there's a characteristic angle, and that's the Einstein radius. And so for a typical microlensing event, this happens to be around 3 AU, and typical timescales for these things are about 25 days, but there are a range of timescales for microlensing events. In one of the plots that Takahiro Sumi just displayed, we saw that timescale distribution ranging from of order a day out to hundreds of days. And so this is because along our line of sight, there's a distribution of lenses. They have a distribution of distances, masses, all kinds of different relative proper motions. And so these things are all conflated and give you a distribution of timescales. But there's information contained in that distribution. And so now I just kind of want to talk a bit about microlensing observables, sort of the routine observables. And yesterday in one of Scott Gowdy's talks, he mentioned there's not really a one-to-one correlation by looking at a microlensing light curve and trying to pick out values like you could do with transits by looking at a depth and measuring a radius and measuring the period. But this is mostly just to show that there is information encoded in microlensing light curves. And so things that you can measure are the duration of the event, so the Einstein crossing time, the peak magnification of the event, and the time at which that occurs. And then if there happens to be a planet, and if you happen to catch it, you can also measure a time scale for the planetary event and a deviation from the single lens magnification, and that also occurs at some time. And because the Einstein crossing time scales with the square root of the mass, if we simply take the ratio of crossing times for the planet to that of the primary and square it, we get the mass ratio. And there's also information about the projected separation into the Einstein radius from these other different observables. But at the end of the day, what we're left with is planet parameters that are relative to properties of the host star. And that's due to the fact that we have this measurement of the Einstein crossing time, and there's degeneracies between the lens mass and distance, as well as the relative velocity between the lens and the source. One thing I want to point out is this is really not different from any other technique. In transit surveys, you measure a depth, which is a ratio of the planet radius to the stellar radius. So you have to have information about the stellar radius. And if we want to know what the masses of these things are, then suddenly you need a relationship between this mass and radius. Microlensing is no different. It's just in a different parameter space. And so if we return to this picture, now it should be clear that there's been some magic that's been done here. I've had to do some kind of statistical transformation from each of these different techniques to even make this plot. But it's still a very useful plot to kind of look at and see where we're at and where we can go in the future. And so for the rest of this talk, I want to focus on demographic studies of M dwarfs. And the reason for this is primarily because in microlensing, the event rate explicitly depends on the lens mass function. And so here I'm showing an expression for the event rate for a lens with given mass and distance and with some given relative lens source velocity along some line of sight. And so this depends on the size of the Einstein radius, the relative velocity. This parameter nu here is a number density along the line of sight, because you can imagine that the more stuff there is between you and the galactic center, the higher the chance is that you will see a chance alignment of stars. And then we also have a dependence on the distribution of lens source relative velocities. And here this term is in fact the lens mass function. And so the terms in here that depend on mass are this Einstein radius, which is again mass of the lens to the 1/2 power. But this lens mass function term here is very heavily weighted in favor of low mass lenses. And so as a result, microlensing most often sees low mass stars as lenses. And so now if we go back to the same picture but plot only the known and confirmed planetary companions for M dwarfs, we see that the numbers get a lot smaller. But we still have good coverage, and we still have a good amount of detections. And so there have been a number of studies in the past that look at these detections and try to infer planet frequencies from them. And so this is showing a plot of planet frequency as a function of mass and as a function of semi-major axis. The green points on either plot are results from rate of velocity surveys. And so they have found quite unanimously that the frequency of giant planets around M stars is quite low. And this is consistent with core accretion models where you expect that to be the case. There has been at least one survey that specifically targets M stars, younger M stars, with high contrast imaging techniques, and they haven't found any planet detections, but can still nevertheless place upper limits on the frequency of giant planets around stars. And these upper limits are consistent with what rate of velocity finds. On the other hand, microlensing has found a frequency of giant planets, although planets that are somewhat less massive than those probed by rate of velocity surveys, but nevertheless still giant planets, that's staggeringly different from rate of velocity surveys. There's this large gap here, more than an order of magnitude difference. And so this blue point is a result from Gould et al. In 2010. And it's hard to understand why these two different results are so different, especially when they probe different physical parameters, they look at different things. So you might be tempted to say, well, microlensing surveys are typically sensitive to separations that are much farther away from their host stars than is rate of velocity surveys. However, one of these points, this darkest green point, is from the Cps Trend Survey that was carried out by Ben Monte and others back in 2014. And what they had done was they had looked at a sample of rate of velocity monitored stars. These are stars that have been monitored for 14 or 15 years. And all of these stars had very long-term rate of velocity drifts or trends. And so this is indicative of the presence of a wide separation companion that's the source of this trend. So what they did was they took those systems and they looked at them with high contrast imaging, and they were able to rule out the presence of any stellar companions and most brown dwarf companions, which means that there's something out there causing this trend. It's not a star, most likely not a brown dwarf. It's got to be a giant planet. And so they used this information to determine what the frequency of planets are, and that's this green point here. And so you can actually see that this particular survey has sensitivity in semi-major axis that goes far out and overlaps with this microlensing point. So what's going on here? That's the question. So this led to a study that I did with Scott Gowdy back when I was a graduate student to compare these two different results. And so I'll just kind of go through the basic methodology here because I think there's a lot to be learned about it, as well as a lot to be learned about microlensing in general. So the idea that we had was to assume that the population of planets that microlensing finds is the very same one that radial velocity surveys are probing. Just assume that from the get-go. And then the problem is to map the properties of those microlensing planets into the space of radial velocity observables, so velocity, semi-amplitude, and orbital period. And then apply the actual detection sensitivities from real radial velocity surveys, or in other words, simulate those surveys on this data, and simply compare with the reported detections. And so what we did and how we define microlensing planets is we assumed a distribution function of mass ratios and projected separations that has this form. So this is uniform in log S and a power law in Q, where the slope was measured by Sumi and others in 2010. And this normalization comes from a combination of the Sumi result as well as that of the Gould survey from 2010. And so we draw a bunch of values of mass ratios and projected separations, and we want to determine what this distribution would look like in the space of radial velocity. And so this is the general flow for how you would do such a thing. You draw your values, and now in order to get a true planet mass and a projected separation in physical units, in AU, we need a few things. You know, we need the stellar mass, we need a distance to the lens, all of these other things. And so we must assume a galactic model as well as a lens mass function. And we need to draw values from a distribution of lenses and other things as well. The problem is that we don't actually know what these true distributions are. We don't know the exact distribution of lens distances to different events. And so what we do to get around this is simply draw from a naive distribution and account for our naivety by weighting by this microlensing event rate. Basically, in fact, exactly that equation that I just showed a few slides before. So that gets us to here. And so now we still need to deproject the semi-major axis. And so in order to do that, we have to generate orbital parameters to finally arrive at our distribution of RV observables. And so when we do that, this is what we get here. You can see that the bulk of the distribution of planets is down here and has a median period of something like 10 years and a median RV semi-amplitude of about 0.2 meters per second, or 20 centimeters per second. So you can already see that a lot of these planets are going to be out of the reach of radial velocity surveys. And in fact, if you plot detection limits for some well-known surveys, such as HARPS or the CPS survey, which are up here, these surveys are only sensitive to things that lie above these lines. And so if you look at the marginal distribution of periods that these surveys are sensitive to, you can see that it almost matches what we find with microlensing. However, if you look over here at the marginal distributions of semi-amplitudes, these radial velocity surveys are really only catching the tail of this distribution. And so you can probably see where we're going from this, but when you apply actual star-by-star detection efficiency curves for each of the stars in these radial velocity surveys, ask how many they'll detect and ask what the properties of those detections will be, you find that it matches with what they actually find. We expected the HARP survey to detect about one planet with a mass between 1 and 13 Jupiter masses in a period between something like 3 and 10 years, and in fact they report one such detection. We do the same thing for that CPS Trend Survey. That's the one where they looked with high contrast imaging as well, and we find very consistent numbers there too, and planets with similar masses and orbital periods. And so going back to this plot, we have shown that although this looks like a very discrepant result, in fact, these are actually very consistent. And it's just so hard to pick one single plane within which to compare different survey results because it's just a lot more complicated than that. And the basic reason for this difference is simply the fact that the microlensing mass ratio function is quite steep. It's very steep. There's a lot of low mass planets, not so many high mass planets. And so moving forward, the next thing that we looked at was including results from direct imaging surveys. So folding that into our analysis to synthesize as many results as we possibly could. And so direct imaging surveys are, of course, sensitive to high mass things on very wide separation orbits. And so this led to another study that we looked at to combine results from 5 different surveys. I'll just sort of very quickly go through this and talk about how the methodology matches up with what we had done before, but is slightly different. So in this case, what we did was we started out by assuming a general model for the planet population, the underlying distribution of planets in our galaxy. Previously, we assumed the microlensing population and used observed properties, use those observations to compare with rate of velocities. Now we're going even more general and saying, okay, now I'm going to just start with a model and simultaneously simulate each of these rate of velocity surveys, each of these microlensing surveys, and each of the direct imaging surveys to get overall constraints on the parameters of this distribution and to even see if the underlying planet distribution around M dwarfs can be modeled by such a function. And so the process is exactly the same, except now we're sort of going in reverse. Previously, we started here and tried to go here. Now we start here and try to figure out what the mass ratios and projected separations are. For rate of velocities, and in particular, since we're interested in long period things, we care about trends. So we need to compute an acceleration in an orbital period. And for direct imaging, we need a magnitude difference in some band, as well as a projected separation, either in physical units or as an angle, and we need a distance for that. So we draw a random distribution and map it into each of these different parameter spaces, simulate each of these surveys, and here I'm just showing examples of detection efficiency curves for these different types of surveys. Ask what they detect and compare with what they actually detect, assign an overall weight to this particular population, and repeat this process many, many times. And when you do that, you find that, in fact, this very simple power law distribution can be used to model the planet population around M dwarfs and is consistent with all of these different types of surveys. And so here I'm showing the joint distributions of these different types of parameters. And here's the marginal distributions for each of these. And you can see that we can constrain the slope of the mass function quite well and the normalization of the entire function. However, there's a degeneracy between the outer cutoff radius of the distribution and the slope of the semi-major axis distribution. And so we derived the median values and 68% uncertainties limits for this, as well as the full posteriors, and show that this is possible. So now this becomes a very powerful tool, and this is really what I want to focus on. This is the M dwarf exoplanet census. This is the best that we have right now. It combines results from all kinds of different surveys, and it's only going to get better. And so here, the color scheme is darker colors represents a higher planet frequency, and lighter colors represents a lower planet frequency. And there's squares with all different kinds of symbols and things. So empty squares or just plain squares indicate regions where we have a good measurement. Squares where we have this sort of positive sloping lines indicate areas where we have an upper limit. And so this is regions where surveys that we've included do have sensitivity but simply don't detect anything. There are squares where we have negative sloped lines, and these are regions where we only have a lower limit because we only have excuse me, limited sensitivity within these particular regions. And there are regions, of course, where we have these vertical lines where we have zero sensitivity and are forced to extrapolate our results. And so I wouldn't trust these areas at all, but just to make it a nice square plot, I've included it anyway. And so future work and how we can improve this and learn more about exoplanet demographics and further the study. One thing is to include results from Daisuke's survey, the MOA survey that looked at a bunch of events and determined this mass ratio function. I won't re-go over that because he just went over it, but so folding this in, because this is now the most complete survey that's been done with microlensing, would be informative and improve our statistics in intermediate separation regimes. And the next thing that should be done is what Scott Gowdy calls the synthesis of the big four. So folding in transits now into everything, and in particular Kepler, to really get the most complete picture of exoplanet demographics that we can get. However, even when this is done, if we look at where the solar system planets fall on here, we're still not quite capturing the entire solar system. So while we know that not every planetary system is like ours, in fact, if it were, Kepler would have found basically nothing. But answering the question of how unique is our solar system, how weird is it, that's something that is still unprobable right now. However, the good news is that in the future, and in particular with WFIRST, we will then have sensitivity to cover most of the solar system and start to answer this question. But the only way you can do this is if you know how to combine results from these two very different types of surveys. And so the question is, how would you do that? So I presented two different ways that you could, two different sort of methods to approach this problem. One would be to assume, for example, let's take the Kepler population and assume that it's the same as the microlensing population in this region of overlap. Do this statistical mapping and compare the results and see if they're consistent. If they are, great. What you do is you take results from Kepler and WFIRST individually and you smash them together and you have your census. Another way to do it is to go back and to do this other approach where you assume a general model and simultaneously re-simulate both of these surveys to constrain the parameters of that model. Those are two ways, but they both have different drawbacks to them. In the case where you want to compare them where they overlap, if it turns out that they're not consistent, then you don't really know how to combine them in that region of overlap. If they are consistent, then great, but you're still sort of left with the same sort of coarseness of bins that you had before. So if we go back to my census here, you can see that this covers 5 orders of magnitude in orbital period and 4 orders of magnitude in planet mass. But it's still quite coarse. We only have decade bins in each of these things. We'd like to have more finer resolution. And so when you do this thing where you smash them together, you're kind of stuck with that. And in the other method where you assume this general model, you have to come up with a model. So how do you pick what model? You could try a whole bunch of different ones and compare them, but really it's hard to motivate that from first principles, from physics and things like that. So my ultimate vision for how you would actually do this is to do something completely different. And this is sort of related to what Daisuke was doing by comparing population synthesis models to his microlensing results. And so what you would do is, you take some population synthesis model, and the inputs to this are some set of initial conditions and some set of input physics. So for initial conditions here, I'm referring to disk masses, disk lifetimes, surface density profiles, temperature profiles, you name it. And for input physics, there's some migration mechanisms that you choose, some rates for those, sources of turbulence, core accretion rates, and again, another multitude of things. And so rather than assuming anything, let's just try to create it from our models. And so in the case of initial conditions, we have actual observational constraints. We have measurements of disk masses, and we have uncertainties and distributions of those things to put in. And so on the front end, we bracket with observations. And input physics, we can simply choose one and then reiterate over them in the end to find out what the best set is. So for each iteration, we produce some distribution of planets. And we then go back and re-simulate these two other surveys and see how close it is or how different it is. So we completely skip the part of having to come up with what a model is and just let our understanding of the physics determine that for us. And in this way, we bracket the problem from both ends. We have observations here, and we have observations here. And there's minimal assumptions that go into this, although there's a ton of them in particular with input physics. That's what we want to learn. We want to learn how planets form. We want to learn how they evolve. And ultimately, I think that this is probably the best method to do that. And in addition to that, we get planet occurrence rates for free. Because what we can do is we can take our best models, make these outputs, and simply compute the occurrence rates. If we want to fit a function, now you're fitting a function rather than assuming a form. And yeah, I guess that's basically all I wanted to say. So I can either continue. I did include some stuff about timescales, but maybe I'll pause and see if there's any questions. And if not, I can do a little bit more on timescale distribution. OK.
Do you like the census plot?
Which one?
The census plot?
Oh, yeah. And so addressing the question of trying to fit the observed timescale distribution with bound planets, in fact, what we did was we took our models where we combined everything together in our distribution function there and did that exact thing. And so I have plots at the end, unless there's a question on this particular slide. Okay. Okay. Yeah, so here, this is showing the timescale distribution that Sumi had published back in 2010. This red dashed line is the lens mass function, so stellar lenses, brown dwarf lenses, et cetera. And this dotted red line is sort of the best that you can do with bound planets. So you do explain a few of these short timescale events, but there's still some discrepancies. You can't push it up too high, because if you push it up too high, you come into conflict with direct imaging, where you predict that they should see a bunch of them and they don't see any. And so this shows the same thing, but with the confidence interval on those fits. And so if you look at the fraction of short timescale events that can be explained by free-floating planets, you find that something like 65 or 70% can be explained. It also depends on what you assume about planet evolutionary models from a direct imaging standpoint. But you can determine what fraction of those events can be explained by bound planets. And in order to turn that into a number of free-floating planets, say per main sequence star, you have to know something about the mass function of those free-floating planets, for which we really have no information. But what you can do is then, again, assume something about the mass function. So if I assume that the mass function is a delta function at some value, say 1 or 2 Jupiter masses, then you can get a number of free-floating planets per main sequence star. And that's what this is showing here. And this is sort of pushing the limits of what's allowed by these different surveys. So yeah, that's basically it. And I guess that's all I had. Yes, absolutely. That's something that I didn't include in this talk, but we did consider in the paper. So really, any property that has a galactic gradient that affects planet frequency is affected, goes into this analysis. So in effect, what we did was essentially ignore differences in host star properties, but we did investigate it. And so what we did was we developed a method to include results from the SDS-S3 apogee experiment, which measures the gradient of metallicity. So they have estimates of metallicity as a function of galactocentric radius and height above the plane. And so while you can't use that to estimate the metallicity for any particular microlens, for the population as a whole, statistically, you can actually get an idea. And so what we did was we folded those apogee results into our simulations to get metallicities for all of our sample. And then what we did was we took the relations, the giant planet frequency metallicity relations that are measured by rate of velocity surveys, and folded that in as well. And so we took those metallicities, applied that relation to figure out what rate of velocity surveys would predict for the population that microlensing probes, taking into account their metallicities. And what we found was that sort of an opposite problem, where those rate of velocity relations predicted that microlensing should see a factor of 20 or 30 more giant planets than they actually did. So it sort of way overestimated it and went in the opposite direction of what we initially thought, which was that microlensing was higher. So it's a mystery, and I don't really have a good example, a good reason for that. I have some ideas. Perhaps this giant planet frequency metallicity correlation is also a function of planet mass itself, such that those things hold for maybe Jupiters and super Jupiters, but when you get down to Saturn mass things, Neptune mass things, it's different. And there's some tentative evidence for this from the HARP survey, where they found that it seems to flatten out a bit for the lower mass things, but they only have very few detections to work off of, and it's tentative at best.